In this section, we're going to learn how to solve linear programming problems geometrically and or graphically, however you want to say it. So it's basically the same thing. So let's start with an application. There's a ring company here that sells two types of ring, brass ring and aluminum rings. And they can produce up to 24 rings each day. So notice it says up to 24 rings each day, using up to 60 total man hours of labor per day. And notice it says it takes 3 man hours to make a brass ring and 2 man hours to make each aluminum ring. How many of each type of ring should be made daily to maximize the company's profit? If the profit on a brass ring is $40 and profit on an aluminum ring is $35. Now again, here it tells you what the variable should represent, how many of each type of ring. So we'll let X be the number of brass rings that's manufactured, and we'll let Y be the number of aluminum rings that's manufactured. Now if you want to, you can set up a table where you know you've got to have the maximum number of the maximum number of rings that you can manufacture per day is 24. So that means that the total number of rings manufactured must be less than or equal to 24. And the maximum number of hours that are available is 60. So that means that the number of hours that are utilized has to be less than or equal to 60. Now this allows you to actually, if it's more profitable, it allows you to actually manufacture less than 24 rings, and it also allows you to use less than 60 hours. So unlike the last module where we were doing equations, here we have inequalities. Now the rings, we have if X is the number of brass rings we make and Y is the number of aluminum rings we make, then we know the total number of rings must be less than or equal to 24, so that would mean that X plus Y would have to be less than or equal to 24. And then since it takes 3 hours to make a brass ring and 2 hours to make an aluminum ring, then 3x is the number of hours to make brass rings and 2y is the total number of hours to make aluminum rings. And if you add 3x to 2y together, that's your total number of hours, and that has to be less than or equal to 60. And then finally, also x and y has to be non-negative because you cannot produce a negative number of rings. And then the objective function is given from these numbers here. So we know that we're going to profit $40 per brass ring and $35 per aluminum ring. So our profit function is 40x plus 35y. If you put all this together, you get a linear programming model. So here we're maximizing P equals 40x plus 35y. We always write the objective function first, and then subject to just tells us what constraints we are subjected to, and we're subjected to these two constraints: x plus y is less than or equal to 24 and 3x plus 2y is less than or equal to 60, and then of course we have our non-negative constraints. Okay, now after we get the model, we need to graph the feasible region. So if you were to graph the inequality x plus y is less than or equal to 24, we talked about how to do this earlier. You find the intercepts. So we would have 0, 24, which is right here, and then 24, 0, which is right here. And then we would draw a line that connects the two, like that, and then we would shade either this side or this side. So the way we're going to determine which side to shade is, remember, we're going to test this point 0, 0. And if you plug 0, 0 into the inequality, you get a true statement. 0 is less than or equal to 24. So we would shade everything below this line. Okay. And actually, even though you can't see it, that's the kind of the pinkish looking region plus all of this over here. So everything below this line. And then to graph the other the other inequality, 3x plus 2y is less than or equal to 60, you graph the boundary 3x plus 2y equals 60 by finding the intercepts. Well, the intercepts for this boundary is 0, 30, and 20, 0. So 0, 30 would be right there, actually right in here somewhere, and then 20, 0 would be right here. So there's 20, 0. And then so you would then draw the line through those 2 points, and then you would try to test your origin again, 0, 0, and when you plug 0, 0 into that one, you get a true statement as well. So if you shade everything below both lines, because that's what you end up doing, so if you look for the overlap of the region that's below both lines, then what you're going to get is a region that looks something like this. It's going to start here, and then it's going to turn down here, and you're going to have everything shaded below it. So you'll have, all of this region here shaded. So I've already got it shaded. You can see the darker green area is the shaded region. Okay, now, but right now I haven't brought in these two yet, where x and y is greater than or equal to 0. If I bring those two in, then that actually restricts this region to the first quadrant. So basically what I'll get is a region that looks something like this. So it's blocked there by the y-axis, and it's blocked here by the x-axis, and it's blocked from there to there by that line, and it's blocked from there to there by that line. Okay, so now you can see the region would be this area in here, which of course includes the boundaries. Now, 3 of these corner points we actually knew from graphing over here. Like we know this is 0, 24. We know this is 0, 0. We know this is 20, 0. And then to actually find this point right here, all you have to do is solve this system of equations right here, because this point is simply the intersection of those two lines. So if you do that, you'll get the point 12, 12. So you actually have 4 corner points, 0, 0, 0, 24, 12, 12, and 20, 0. And so there's your corner. Now we know the fundamental theorem of linear programming tells us that all we have to do is plug these corner points into the objective function, and whichever one of those corner points gives us the maximum value for p, that's our solution. But let me just take a few minutes to show you why we only have to check the corner points. The reason we only have to check the corner points is, first of all, this objective function 40x plus 35y equal p, it's actually a linear function. P is just some number, but I don't know what it is. So now let's solve this for y. If we subtract 40x from both sides, we get 35y equals minus 40x plus p. And then if we divide both sides by 35, we get y equals minus 40 over 35 x plus p over 35. And so basically what we get here now is we get a linear equation that has a slope of negative 8 over 7 and has a y-intercept of whatever p over 35 is. Okay, well, let me just kind of summarize what happens here. So if you were to graph that line, let's say that you graph the line for, if p is 1400, let's say you said, well, why don't we let the profit be 1400? Well, if you let the profit be 1400, then this line that has this negative 8/7 slope would cross the y-axis here at 1400 divided by 35, which would be at 40. So your objective function would actually go through here. But the problem here is remember, this is the feasible region. The solution has to be in the feasible region. So what happens is as you lower, let's say we lower this value, let's say we lower it to 700. So if we lower it to 700, then 700 divided by 35 would be 20. So then my graph would lower to, say, somewhere in here where it crosses the line 20. Okay, so now there's lots of points in the region that fit that line, but the problem is I actually went farther down than I had to. So the question is, how far do I have to go to where I get the largest value for P and still remain in the region? So you just go low enough until you hit the region. And notice that you would hit the region at what? At a corner point. So we hit this region first at this corner point. And so that's the reason that we only have to check the corner points. And so that's why the fundamental theorem of linear programming says that if an optimal solution exists, it must occur at one of the corner points. So I won't waste any more time going over that, but you can read the notes if you need to read the rest of this. But now all I have to do is to check each corner point. So you'll remember that one corner point was 0, 0. So if I plug 0, 0 in here for x and y, you'll just get 0. And one was 0, 24. So if you plug 0, 24 in here, you'll just get 35 times 24, which is 840. And if you plug 12, 12 in here, you actually get 40 times 12 plus 35 times 12, and that's going to give us 900. And then if you plug 20, 0 in here, you're going to get 40 times 20, which is 800. So since the solution must occur at a corner point, then we just pick whichever one of these corner points that gave us the maximum value. And so it looks like we get a maximum value of 900, and that actually occurs when x is 12 and y is 12. So that tells us that the optimal solution is a maximum profit of $900 when we manufacture 12 brass rings and 12 aluminum rings. Okay? Now, don't get caught up on thinking that it always must be a solution that falls within the within the region, or in the first quadrant here, because your solution could very well have been this point 0, 24 or this point 20, 0. Okay. So we'll solve more linear programming problems by graphing in the next video.